All right, look at section 1.3 as we look at the topic of linear functions. So we just finished defining a function, right? A correspondence or relationship between two sets. The sets that we're usually dealing with, we're thinking about ordered pairs, equations, x and y, those two relating variables. Well, the relationship in a function is each x gives us exactly one y. With that said, we're going to look at a linear function, the graph of a line. All right, we're going to talk about slope, which defines your lines, and some applications of that. So in a linear function, we've got a function of x of the form f of x equal to mx plus b, right, where m and b are constants. So with this, we talk about our slope-intercept form, right? We've seen y equal mx plus b form before. So this is our slope-intercept form for a linear function. And of course, characteristics of this linear function slope-intercept form is our domain variable x, our input variable, is a first-degree variable, right? It means it has an exponent of 1 on the variable x. And with that said, when we graph it, of course, it graphs a line. So again, a linear function graphically graphs a line. And we talk about the characteristics of that line when we get into slope. Tells us the direction, whether it's increasing, decreasing, horizontal. We'll know from the slope what our line will be doing graphically. Now, m and b, as we've said, represent these constant values. Now, m, which is the coefficient of x, defines slope. So m is slope, and b, the constant term added to the x term, as long as you're in y equal form, y equal mx plus b form, locates your y-intercept. So the point 0b, right, would be the point at which our graph will cross through the y-axis. So again, m references slope, and our y-intercept referenced by the value of b. So with that said, let's take an example. Let's find the slope and the y-intercept of the following equation. So again, let's put it in slope-intercept form. So with that said, we're looking at y equal form. So with slope-intercept form, we want y equal mx plus b form. So we got to solve for y, right? So that's our first step, right? We got to go get y equal. So locate our y term, and let's go ahead and solve it. As we do that, we will move the x term over, and we'll move the minus 7 over. So we can subtract a 3x on both sides, apply the addition property equality to move the x term, and we can add a 7 on both sides to move that minus 7 over. So as we do that, we're isolating, of course, our y term. So that implies negative 6y is equal to negative 3x plus 7. And then, of course, our last step, to finish off y equal form, again, our goal is y equal. We need to divide out the negative 6 on both sides of the equation. And as we do that, we get our slope-intercept form for this linear function. Let's go ahead and reduce. Negative 3 over negative 6 is going to reduce to 1/2. So we have 1/2 x. 7 over negative 6 is minus 7/6. So y equal 1/2 x minus 7/6 is our slope-intercept form. With that said, let's go ahead and identify the slope. So our slope, which is the value of m, right? So again, here's y equal mx plus b form. So m is 1/2, and the value of b, right, which will tell us about our y-intercept. So our point at which our graph crosses the y-axis is the ordered pair 0b, which is the point 0, negative 7/6. It's our y-intercept. So there's our slope, right? And here's the y-intercept point. So m is 1/2, and y-intercept's negative 7/6. And now I want to talk about what the value of 1/2 actually tells us with our line. Let's define slope. So it says the slope, m, which abbreviate math, slope with m. We've got the slope m of a non-vertical line. So we don't define slope on a vertical line. So it has to be a non-vertical line. So a slanted line or horizontal line, we can define slope. With that said, it passes through the following 2 points. So we pick 2 points on this line, this non-vertical line. Point 1, we can label the coordinates x1, y1. Point 2, x2, y2. It says M is defined as the rise and the run between those 2 points. So any 2 points on a line, we want to look for the rise and the run between them. And this is a constant value. It doesn't matter what 2 points you pick. Slope is a constant value. Again, it does not change. Right? A line has that same rise and run between any 2 points on it. And of course, rise means how far up or down did you move from point 1 to point 2. That's what the numerator of our slope tells us. It tells us the vertical distance, how far up or down. And to find that algebraically, you're going to find the change in the y values. So y2 minus y1, the difference in y coordinates, will give us the rise factor. And the denominator of slope, again, slope is defined as this ratio of rise to run. Run is how far right or left you move, the horizontal distance, the change in the x values, right? x2 minus x1, right? Difference in the x coordinates. So with that said, again, that defines slope. So with slope, you're talking about your formula, y2 minus y1 over x2 minus x1. So there's your slope formula. Now, with that said, if we have a positive slope, so if m is greater than 0, we have a increasing line, right? We have a line that rises from left to right. If our slope is not positive, then it could be negative, right? It's 2 other conditions. So either going to be negative or 0. But if m is less than 0, it's a negative value for your slope, you'll have a decreasing line, right? We'll have a line that drops as you move from left to right, decreases in values. You're going along the x-axis from left to right. And then if you had no slope, so we can add that to it. So no slope, which means m is 0, we have a horizontal line, right? We have a line that stays the same as we move from left to right. So graphically, we're looking at a horizontal line there, no slope. So that's your definition of slope. So let's take that into example. It says here in example A, to find the slope of the following lines. First line here, we've got information that passes through the following 2 points, -6, -1, and 2, -13. So what I'd like to do first is to go ahead and draw in my x and y axis, right? And let's just draw a picture of this line. So as we go -6, less 6, down 1, right? We're over here in quad 3 with this ordered pair. And then we go right 2, down 13. We'll be down here in quad 4, right? 2, -13. And we can go ahead and connect these 2 points to see a graph of this line. So there's your graph passing through those 2 ordered pairs. So we know from that graph, this is a decreasing line, right? This graph, as you move from left to right along the domain, it's going down, it's decreasing in value. As x gets larger, y gets smaller. It's moving down, it's decreasing. So with that said, we know m is negative, right? This is a decreasing line. So with that said, let's go ahead and find that value of m. Let's find that constant. So to do that, remember, definition, m is your rise and your run between any 2 points. So let's take a look at the rise and run. So let's go from point 1, the first point, -6, -1. Now as we're moving to point 2, we're going to have to go down on the y-axis, right, and then to the right. So you see our rise factor, right, here's your rise factor. Now how far down did we go? So again, this is the rise, right, in our graph, the vertical distance, how far we're traveling down. All right, let's go ahead and look at that. So we can all see that looking at it. We've gone from -1 on the y-axis down here to -13. So that means we've gone down 12 units, right? That's our vertical distance. There's the rise factor, down 12. And then what's our horizontal distance? How far did we move across on the x-axis? So we went from -6 to 2. So we went right 8 units. There's your run factor, right? The change in the x-coordinates, right? And that's your run factor, your horizontal distance. So as far as slope goes, your rise and run, we get -12 divided by 8. Down 12, right 8. That's your rate of change, right, from point to point. That's your constant value, your slope value. As we reduce that, let's go ahead and reduce. We divide out our common factor 4. It reduces down to -3/2. So there's the value of m. There's your slope. Now, of course, you could also use the slope formula, but I wanted to show it to you looking at it. So let's go to our formula that we just established earlier. Right, m, again, being rise over run, right, is equal to y2 minus y1 over x2 minus x1. So that's -13 minus -1 divided by 2 minus -6. As we simplify, so let's go ahead and take care of the double negatives. We know 2 negatives, right, make a positive. So we end up here with a value of -13 plus 1, right, as we subtract the -1. So that ends up -13 plus 1 divided by 2 minus -6 ends up as 2 plus 6, right, double negative. And we get what? -12 over 8, which reduces to negative, what, 3/2. So again, there's your value of m, your slope. So you see it there plugged into your formula. Of course, you can see it there in your graph also. But yeah, we have our slope formula right here. y2 minus y1 over x2 minus x1. All right, let's take that and apply it to our next problem. Let's apply this definition of slope. Now, in the next problem, a little different. Instead of giving us 2 ordered pairs with real number values, we've got some variables representing the coordinates of these 2 points, variable expressions. So point 1 is labeled with the ordered pair of a, there's the x-coordinate, and 3a plus 1 being the y-coordinate. So if you want, we can go ahead and label that x1 and y1. And in point 2, we've got a x-coordinate represented by a plus h, call that x2, and the y-coordinate of point 2, I'll call that y2, is this expression of 3 times a plus h plus 1. So slope, so let's go to our definition. Slope, again, your rise over your run between any 2 points. So y2 minus y1 over x2 minus x1. So let's go ahead and plug that information in. So y2, so 3 times a plus h plus 1. So all of that, and again, if you want, we can put that in parentheses. All of that represents the y-coordinate, right? There's the value of y2. And as we subtract from that, so minus y1, so let's go look at, and I'll put it in parentheses, what represents the y-coordinate of the first point, which is 3a plus 1. Right? And then the close out the parentheses. So there's the y-coordinate of point 2. So we'll go ahead and put it in the same color of the parentheses with blue. So there's your numerator, right? There's the change in the y-coordinates, y2 minus y1. So there's your rise factor with these 2 points involved, all divided by the change in the x-coordinates, your run factor. So with the denominator, we've got our x-coordinate from point 2, which is represented by the value of a plus h. So go ahead and plug that in. And then again, minus, and let's keep this parentheses in the same color. All right, so all that represents, again, the x-coordinate from point 2. So again, I can label that below it. There's x2. And then minus, again, the x-coordinate from the first point, which, again, the x-coordinate from the first point is just a. So we're subtracting a here from that. So again, using our slope definition, right, there's our slope value. Now we need to simplify that. We're not going to leave that as our answer. So we need to work on making this look better. So let's go ahead and do that. Let's go ahead and distribute. For example, what's 3 times a plus h give us? That gives us 3a plus 3h plus 1. And then we'll distribute the minus sign through. So that's a minus 3a and a minus 1. All divided by a plus h minus a. Okay. And that simplifies nicely now because we see some like terms coming into play. So we've got a 3a and a minus 3a. We've got a plus 1 and a minus 1. They cancel out. And denominator, the a's cancel. So it's simplifying nicely. We're left with just 3h divided by h. And then, of course, we can divide out the common factor of h. And here's our constant value for the slope. Our slope is 3. So there's your rise and run between any 2 points. Up 3, right 1, positive slope, right, increase in line. So just keep in mind, again, with m being positive, it's a increasing line. So characteristic from that. All right, moving on. Let's go to characteristics of your horizontal and vertical line equations. Slope characteristics. So we're defining lines based off the slope. Now, the horizontal line we mentioned earlier, that's a line with no slope. A slope of 0. So in a horizontal line, m is 0. And why is that? So you see in the notes, we go back to our slope definition, the rise over your run, the change in y with change in x. Well, in a horizontal line, you're not going up or down. You have no rise factor. You have no difference in the y coordinates. So your numerator is going to always be a value of 0, right, on a horizontal line. Now you're going to have change in x values because we're moving left and right. So change in x, yeah, there's going to be a change in x, but 0 divided by anything, right, will be 0. So our slope, again, on a horizontal line is 0. So I want to keep that in mind. And now let's go to the equation form. So using slope-intercept form, y equal mx plus b form. So m is 0. So what happens to our x term? 0 times x is 0. So we come up with our equation of the form y equal b. And of course 0b being the y-intercept. So there's our equation, right? A horizontal line equation, right? In slope-intercept form, right? Y equal b. There's no x term, right? Because there's no slope. So horizontal lines, no slope with the characteristic there. It's, again, not going up or down. It's horizontal. Has no rise factor. Now, in a vertical line, right? As we look at a vertical line, we have what we call undefined slope. So we don't define slope on vertical lines. We only define slope on non-vertical lines, increase and decrease in horizontals. And the reason for the undefined slope is the vertical lines going up and down, not right and left. The change in x, the run factor, will always be 0. And you cannot divide by 0, right? Dividing by 0 is undefined. So again, vertical lines going straight up and down, again, no run factor. Horizontal lines, there's no rise factor, right? Change in y is 0 on a horizontal. Now, equation form, now these are not functions. So vertical line definitely doesn't satisfy the definition of function where each x gives you one y, right? Vertical lines, x is constant, y is always changing. So you got infinite outputs for the same x. Now, in the equation form, it's x equal to your constant value of, say, k. So where k, 0, would be the x-intercept. X equal k would be your equation form. So again, horizontal lines, y equal b. Vertical line equations, x equal some number k. Undefined slope. So let's take and put all that together as these last few examples. It says determine the slope if it exists. So if it's a non-vertical line, we can determine the value of the slope. And then graph the line. So I've got an example of each type of line we could run into. Now we see here in example A, right, x equal 3, we've got a vertical line equation, right, x equal to a constant. So as we talk about slope, m is undefined. All right, so let's go ahead and graph that. So down here, let's build a graph. We'll show all three of these together on the same plane. So if I want to graph in x equal 3, right, I can go over here to 3 on the x-axis. Let's plot the point 3, 0. And I can draw in the vertical line here at x equal to 3. So here's the graph of x equal to 3. Right, so again, any point on this line, right, we'd have here, say that's the point 3, 5. Down here is the point 3, negative 3. Right, again, we can put as many points as we want. Let's go ahead and look at relationship of the ordered pairs. So again, what do we know about x? X is always equal to 3. There is no run factor. So if you're using slope, right, what would happen? So if you were taking the 2 points here, 3, 5, and 3, 0, when you go to your denominator, 3 minus 3, you get 0. You can't divide by 0, undefined, right? Undefined slope with that. Now let's go to our example B. We should quickly be able to tell what we're dealing with. Right? X equal constant is a vertical line equation. Y equal a constant is a horizontal line equation. So no x term. And the reason there's no x term is because there's no slope. So our slope is 0. So no slope. And with that said, we could go ahead and graph that quickly. So let's go down here and look at the ordered pair 0, negative 4. And let's graph in. I'll graph it here in blue. Here's the line y equal to negative 4. So those are quick, easy lines to graph, right? Your horizontal line and your vertical line. You only need 1 point. But if you want to put other points on there, let's put the intersection point with vertical line. We know this would be the point 3, negative 4. But we know on this y-axis, right, y is always equal to negative 4 at y equal negative 4's graph. Now let's go to the third equation. And in the third equation, all right, we've got an equation in slope-intercept form. We've got a x term, right? We're talking about a decreasing line, right? M is negative 2. So that applies decreasing line, negative slope. So we graph this line, right? It's going down from left to right with a slope of negative 2, down 2, right 1. So again, there's our characteristic, right, when m is less than 0. And of course, our y-intercept, let's go ahead and write the y-intercept point. Y-intercept point is that ordered pair 0, 6, right? There's the value of b. So we had slope-intercept form, right? We had a slanted line. So we have our x term. So as we go ahead and graph that, let's go ahead and plot the point 0, 6. And let's use the slope. So here's a good application of slope. So if m is negative 2, let's write that as a fraction. So here's our rise, right? And here's our run. So that implies what? Down 2, right? Negative 2. And then run, positive 1, right 1. So there's the slope, right? Down 2, right 1. So down 2, let's plot another point. We'd be at 0, 4. And then, of course, right 1, we would be at the point 1, 4. Right? And then you could graph in this line. So there's the graph, right, of y equal to negative 2x plus 6. So you can see all three of them together, right, with this rectangle coordinate system, putting them here on the xy axis. So that's definition of linear functions, and they're defined using slope. So slope tells us everything about a line. So what type of line we're dealing with, and then we can use slope, of course, to graph it. All right? So I hope that helps you here with section 3.